I hope we are all good, and then so far so good. I'm glad I had some students coming to see me regarding the videos I make and how helpful it has been to them. And so the motivation for this series of videos is such that if you miss something in the lecture hall, you can come back to these videos, play them over and over again to understand. Or if you have the chance to have the videos before the in-person lectures too, then you can fill in some potholes. And so I try my best to make the videos as short as it can and then as brief as my talks can be before we meet in person. And for today's video, I'm looking at the second method for solving higher order differential equations. Over the past few days, we are considering a linear equation which is either homogeneous or non-homogeneous, and then they are of higher order, and then lastly they are all of constant coefficients. We've treated that of a homogeneous case, and we did one aspect of the non-homogeneous where we said you can use a method of undetermined coefficient and variation of parameters. And so we are dwelling on variation of parameters here. So I'll quickly go through my slides here. On slide 32, it says if I have equation of the form equation 9, that is a non-homogeneous because I have the source term not equal to 0. When that is done, we've already classified when to use VMOU. When you have polynomials, when you have exponentials, and then when you have some sines and cos, you can use MOU. Now VOPs are extension, so I use a keyword. They are extensions of the class of GTs. So someone would say they are generalizations of GTs or the source term. Don't forget this is a source term. It means that the source terms that MOU cannot solve or cannot deal with, the VOPs help us get it done. This is also to imply that, as you can see my figure here, it says can I use VOP to solve classes of MOU? Yes, that is because VOPs are extension. It means it can do what MOU does and then more. So how does the VOP works? So I'll give you a clear distinction between these two. Let's look at MOU and then VOP. We've already established the class of GTs. Now realize that we always want to have the homogeneous part. It means setting the differential equation to 0. The same thing for VOP. We always want to set the differential equation to 0 for the complementary solution. Under MOU, we said our YP is a copy of our source term such that the solutions of YP should not be seen in the solutions of my complementary. The difference here is that for variational parameters, our YP is rather a copy of the general solution or the complementary solution. That is the difference here. If I'm done here, I have to differentiate, substitute, and then I compare coefficients. Now what do we do under VOP? We still differentiate and then substitute. The last difference here is that after substitution, we can't easily compare coefficients because we'll end up getting the resulting here will be some systems of equation with some underlying assumptions done. So in this, I wouldn't go through how to get the systems of equation. What I'll do is to show you how the systems of equation evolves. So don't forget the steps. You always find your YC, your YP is a copy of that, and then you end up getting some systems of equations. So let me quickly take you through the illustration. Assuming I solve a problem and I have a solution of some C1 y1 of x, C2 y2 of x through to some cn's. This can be exponential, it can be anything, but I'm just representing them like this. It means my yp is a copy of that, so I have it as that. What can we tell or see here? Realize that I've just replaced the constants here by some variable use, and so this is what you differentiate. For the differentiation here, we differentiate it n-1 times. Unlike MOU that you have to differentiate respect to the order, here we differentiate it n-1 times. Let me put it this way. So this n to the power n times, this n-1 times. If you do that, you end up getting a system in this form. You have some u1 prime y1, that's the first part of the solution. So I'll just write two elements, then move to the last end, is equal to 0. The second derivative becomes u1 prime of x, the first derivative, the second derivative. Check the pattern of how the systems will look like. I didn't go through how to get a system, but it would always follow a certain pattern. If I want the third derivative, it becomes y2 prime prime, so y1 here, sorry, through to the last term equal to 0. This is how the pattern will be. So assuming I have it to the last end, it means I have yn of some n-1 times, and then the second part remains with n-1 times, but at the last bit of the derivative, you're going to get the source term over a. Now it is, don't forget your linear equations of this form: p of x y n-1, q of x y is equal to some gt. This is where your a is coming from. It means if there's the coefficient here is not equal to 1, you must divide through by what? The a. So that is how come you have this 1 over the a. This is how the system would always be like. So the question is, how do I solve this system of equation? So I'll use a different pen here. You realize that I can use matrices. If you've done linear algebra, I can write this out in the matrix form. Matrix means write the coefficients, have your unknowns here, equate it to what the right hand side. My right hand sides are 0, 0, 0 through to some gt's over a. What are my unknowns? I have some u1 prime, u2 prime, u3 prime. So I have it as u3 prime here, and then through to the last one, un prime. And what are the coefficients? The coefficient, if I pick the first row, the coefficient here becomes y1, y2, y3 through to yn. The second row, it takes the derivative. The third row takes the second derivative. And then we'll take the last row. That one becomes, so let me extend the matrix. So the one last one becomes yn to the power n-1, y2 n-1, y3 n-1 through to yn n minus 1. And so I guess I have to do the correction here. So the subscript remains to n. Yeah, that is now correct. And the question is, how do you solve a system of equation of this form? Someone will say, this is the same as some ax equal to b. Someone will say, I'll use Gaussian elimination. Well, you would realize that your primes, your derivatives will be a mixture of variables. These derivatives here, the n minus 1 will be some variables and then some constants. If they were constant throughout, then you are good to go with the Gaussian elimination or any other method you know. So it means that I would have solved x equal to some A inverse of B. I would have just find the inverse of the matrix A. But this will be difficult to do because of the variables that will be involved. So we go ahead and use the solution method called the Cramer's rule. If you immediately hear of a Cramer's rule, you know what comes to mind: the Wronskian. In this session, I'm not going to go through how to use the Cramer's rule, but let's see how I could easily write out my system without any headache. So I'll go to the next page here. Assuming I have a differential equation given and the highest order is 2, so it means that it is prime. You realize that I expect a solution of this form: some c1y1 plus c2y2. Hence, my particular solution will be of the form u1y1 plus u2y2. Before I forget, let me make a comment here. You realize that if I should solve for the x, which is this guy, they are u1 primes, u2 prime, u3 prime, un prime. But my yp's are not primes. My yp's are u's, u1, u2, u3. And so what do I do to get u1, u2, u3? I'll have to integrate this ones to get the u1. I have to integrate u2 prime to get the u2, and so on and so forth. So this is the last thing you go through to able to write your yp's out. If you found u1, then you can replace u1, then your solutions in that order. Okay. Having said that, let me move ahead with my example. It means if this is my assumed yp, my systems of equation, I can easily write it out. You have to differentiate it n minus 1 times. Now n is equal to 2. It means I have to differentiate it just once. So my system becomes the first part of the solution and then its first derivative. The unknowns here is u1 prime, u2 prime is equal to 0 and then gt over a. If your a is 1, you are good to go. But whatever your source term is, you use that. The second example, assuming I have a differential equation and the highest order here is 3. Now n is 3. It means I differentiate it n minus 1 times, which means I differentiate it twice. So my yp will be a form of, so my homogeneous solution, because it's 3, I will expect some 3 answers. And then my particular solution becomes some u1y1, u2y2, u3y3. And hence I can write a system out for this. The system becomes the first terms of the solution and then the second term prime. I'm not done. I can end at y prime. So the last one becomes prime, y2 prime, y3 prime. With my solution u1, u2, u3 is equal to, the first term goes to 0, second term goes to 0. The last term always take the form gt over a. I hope you are getting the systems. Now the last example, if I have a differential equation, it means it is non-homogeneous, differential, linear, whatever, and then the order here is fourth order. I have to differentiate it 3 times. Hence my system becomes of the form, the first state of the solution, the first derivative of the solution, the second derivative of the solutions, 3 times. So this is the third derivative, y2 y prime 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 through to yn prime prime prime, and then the unknowns becomes my u1 prime, u2 prime, u3 prime through to what, my un prime, is equal to, every term goes to 0 except the last term, that takes gt over a. So this is how you write your systems out, and we'll use what we call the Cramer's rule to solve this system. And so that is the cheat table I would want you to have regarding the use of the variation of parameters. So stay tuned for the next sessions on a simple example on how to use a VOP.